Have you ever wished you could peer into the future, to anticipate what's coming next? While we can't quite build a time machine, in the world of data science, we have tools that allow us to make educated guesses, to predict trends based on past information. One of the most fundamental and powerful of these tools is simple linear regression. At its heart, regression analysis is a statistical method used to model the relationship between a dependent variable and one or more independent variables. Think of it as finding a pattern or a connection that allows us to understand how changes in one thing might influence another. Simple linear regression specifically focuses on the relationship between variables, a single independent variable and a single dependent variable. The linear part means we're trying to model this relationship using a straight line. It's about finding the best straight line that describes how one variable changes in response to another. Imagine you want to predict house prices. Here, the house price would be the thing you want to predict. What might influence it? Perhaps the size of the house, which would be your. Simple linear regression helps us quantify that connection. The core of simple linear regression is its equation, which you might remember from algebra, y equals mx plus b. In statistics, we often write it as y equals beta plus beta x plus epsilon. Here, y is our predicted dependent variable, x is our independent variable, beta is the y-intercept, and beta is the slope of the line. The epsilon represents the error term, acknowledging that our model won't be perfectly accurate every time. To visualize this, imagine plotting your data points on a scatter graph, perhaps house sizes on the x-axis and prices on the y-axis. Each point represents a house you know about. Simple linear regression then draws a single, straight line through these points. This isn't just any line, it's the line of best fit. What makes it the line of best fit? It's the line that minimizes the sum of the squared differences between the actual observed values and the values predicted by our line. These differences are called residuals or errors. Essentially, we're trying to draw a line that gets as close as possible to all the data points collectively. So, why is this simple technique so important? It's incredibly versatile. Businesses use it to forecast sales based on advertising spend, economists predict GDP based on interest rates, and scientists model the relationship between dosage and effect. It provides a straightforward way to understand and quantify relationships. However, it's crucial to remember that simple linear regression comes with assumptions. For instance, it assumes a linear relationship truly exists between the variables. It also assumes that the errors are normally distributed and have constant variance. Violating these assumptions can lead to misleading predictions. Once you have your regression line, the slope tells you how much the dependent variable is expected to change for every 1 unit increase in the independent variable. The intercept represents the predicted value of the dependent variable when the independent variable is 0. Interpreting these coefficients correctly is key to drawing meaningful conclusions. While powerful, simple linear regression is just the beginning. Real-world scenarios often involve many influencing factors. This leads to more advanced techniques like multiple linear regression, which considers multiple independent variables, or even nonlinear regression when the relationship isn't a straight line. In essence, simple linear regression offers a foundational understanding of how we can use data to uncover relationships and make predictions. It demystifies the idea of predicting the future by showing us a clear, mathematical path to understanding and projecting trends, helping us make more informed decisions in an uncertain world.